I was just gonna start and look, like if there's a part I don't want to do, I'll just skip it in the practical. So I was gonna start from the start maybe. Like especially the recursive functions, I was gonna like program them because like we could get a random recursive function to write, and then like it might not be something you've done before. So like this one, like sum of reciprocals, or yeah. So they could do like something similar, but then make it, instead of making it squared, they'll make it like, I don't know, cubed or whatever, or just like, or just the reciprocal. But like, or, I don't know which ones I'll skip yet. Like if it goes very fast, I'll get to part like practical 7. If it doesn't go fast enough, I'll like start skipping stuff to get to practical 7. If there's something specifically you want me to go for, I can just start from that. Like there's no problem with that. Like you just find the question you want me to go for definitely, and I'll do that. I'll just make a start. This practical 6, and I've made an empty project here. You can see everything alright, and then I'll create a new file here. That's large enough and all. Is it? Doesn't go blurry, right? The first question then, just create a project called recursion. I didn't call it anything, did I? Ah, whatever. And then the function below is like, it actually does that. It does like this for you. So, but it's iterative, so it goes through numbers from like 1 to n and finds the sum of the reciprocal of a number, reciprocal squared. So when I is 1, you add 1 over I squared, so 1 over 1 squared. When I is 2, 1 over 2 squared, and so on, basically from 1 to n. And what they want you to do is to do it recursive. So instead of a for loop, you're going to use recursion to change the value of I. So I might just copy paste it for reference. I'm sure they said how to name it. They didn't really, but they probably should say how to name it. So for recursion, we definitely, like, the first thing we need to know is like the minimum problem we're gonna solve. So like the minimum problem is like, if 1 gets passed in, what do you return? So if 1 gets passed in, it's gonna be so iterate from, so if 1 gets passed in here, you iterate from 1 to 1, so it only does this once, and you're gonna return like 1 over 1 squared, so 1. So if n is 1, the answer will always be 1. So and then from there on, what you need to do is if it's not 1, what you want to do is figure out the current piece you're working on. So you're like, for recursive problems, you'll usually work backwards. So uh, when you get this, when you get past in like 6, what you do is you start at the 6, you find 1 over 6 squared, then you move down to 5, because it's easier to like stop at like 0 than it is to stop at like infinity. So if you work from left to right, you're going to go off into infinity, whereas if you go from right to left, you're going to move in towards 0 and you know when to stop. So really what you can do also is like check that 0 doesn't get passed in here, or like a negative number. Mm. I'm pretty sure you are, yeah. Did you do plus equals there when you were collecting it? Because if you just do equals, you could have reassigned it, and that's why it was getting reset with each one you do. So then, oh wait, so we have to sum the current number we're on. So 1 over n times n, and this is integer, and n is integer, so n squared is also integer. And basically, if you divide an integer by an integer, it'll give you an integer, so it'll ignore like that this division gives a double. So what we want to do is also we want sum to be double, because we want to store like the fractional part, and we want to cast it. So when you're dividing an integer by an integer, to make sure like the result is double, so you have the fractional part, you would cast like either like the denominator or the numerator to like the type you need. So in our case it's double. So like it always just compiles or like runs from left to right. So it hits this, sees double, so the next thing across it'll convert to a float or like a double, so a decimal number. So what it'll do this, and then it will divide it by the integer, but then because it's already double, dividing by the integer will leave the fractional part in here. Yeah, so you get the fractional part in the answer. So we added the current number we're on reciprocal to the sum, but we also need to add numbers below it. So what do we do? Is we would return the sum plus the reciprocal of a lower number, or like this is the recursive call here. So what it'll do, let's say we've got like 3 passed in here. What happens is we skip all of that because it doesn't go into those conditions. Also could probably move this lower down because it's only used here, it's not needed for the if, so it can be like bunched up with this code here. That's where it's used. If I write it right, if we pass in 3, so n equals 3, then sum, first it equals 1 over 3 squared, and what happens after is sum equals like whatever it is. What we return is like sum plus like the result of this with 2 in, so we would call this of 2. When you call this of 2, what it does is the same thing. So when you call it of 2, the sum, local variable, it's local to the method. So when you call it of 2, it'll have another sum, which you like here you assign it to be 1 over 2 squared this time because 2 got passed in. And what it returns again sum plus the recursive call, and then you reduce n by 1.
So 1 gets passed in, so n equals 1. This is sort of like, if you remember stack frames, this will sort of be happening in the stack. So the first call to this with free, the local variable, the parameter gets stored on the stack. The local variable sum gets stored on the stack. And then it gets changed to like whatever it is plus the result of another call. And then the other call creates a stack frame and gets placed in the stack below it. So, but then for it, the parameter is 2. It stores its own sum on the stack for that specific stack frame for like this specific function call. And then same for this here. So it'll create a new stack frame for the function call. And for 1, we said to return just 1.0. So sum equals 1.0. And from here, because it's our base case, we don't do another recursive call when it's 1. So what we do is we return from the function without calling another one. We remove it from the stack. The result gets placed here. So our result there was 1. Same for this thing. So now we place the result here and we can return. So we were waiting for this result to come back before we return this. So now let's say we're in like where n equals 2. We got the result back of 1. So we can take this and return it. So sum at the moment equals 1 over 2 squared plus the 1. So, alright, this is our new sum that returns from r squared equals 2. R squared with n equals 2. So we return it into the place of this function call. Remove the stack frame. And then for free, what we do is we do sum plus the result. And we return that. And that gets returned like as the answer. So that will be returned to wherever we call this with free. If you do this and free, after you call it, it'll just return this number here. And then you can print it or whatever, or store it in a variable. So theoretically this should work. I have not run it yet. It might not work, so I don't know if it'll work yet. Yep. For what? You don't have to return anything really. 0 is like the default, so it's like no error is 0, and 1 is like some error occurred. And then, but then you can like think of a specific code. I think there might be specific codes like C++ has that it returns, but you could think of your own code to like so that you know what error. So you could create your own error code that only you know like what error it is. As always, I like copy pasting stuff. Let me check that I'm recording. Yeah, still recording. It's all good. Yeah, I'll do the 5, but then I've also got the original function they gave us, so I can compare it. So namespaces we need to include. Where did you declare it? Just here? Or yeah. You don't need to. I you if you declare it here, you want to cast it. It used to be a 1 like this. So if I run it now, you'll see that the answer is different. So So you see, this is the first one, just their function. So it works fine, or whatever it gives. I'm not sure if it's right. And then this result, because we did not cast this 1 to a double, the result of the division is just int by int, which gives you an int. So what we do is we cast this into a double, then this becomes double by int, which will give you double. So you can either just cast it double, or if you write 0.0, like the compiler interprets it as a double. So like this instance, like value will be interpreted as a double.
That seems a good way to find an error in your code later on.
Yeah, so might as well cast it. So now it's the same, and like, is it right? Is it not? I think they gave you an example output. Yeah, so just in case, like to go with the thing. Where is it? I thought they had like a value you could test against. Apparently not. I think I used a calculator to test it. Yeah, and also basically with recursion, Stack Overflow, if you make n too large, not sure how large it should be, we can actually test it.
I don't think it can go over 100, can it?
Oh, it went over 100, over 1000. Basically, like in my like Casio calculator, you know, like just general ones used for A level, I think large could go as 69, I think. So you know, for factorial, it's literally a recursive program running in your calculator. So if you, oh, actually, it's not really. It's just more that it can't fit a larger number, I think. Yeah, sorry, that's wrong. Basically, it can't fit a larger number. It's not recursive in the calculator, because that'd be a bit stupid. So like 10,000 might cause the error. Yeah. So 10,000 is too large, and then you could probably, like, if you tweak it, you could figure out the exact value. But it doesn't matter. It's just basically, I don't know. It might ask, like, they might ask you like a difference between like an iterative approach or a recursive approach, but I'm not sure. So you would say that, like, you saw the first one actually printed, but then the second one crashed because the first one does not play stuff on the. It just calls the function once. Like it stores like one param, it stores one double. The other one stores just like each call gets stored in the stack. So we stored like 10,000 times we stored n, 10,000 times we stored sum. And there's also other stuff going along with function calls.
Space complexity higher, or
No, space complexity to do with algorithms. It is not concerned with like the actual implementation in like hardware or whatever. So like for this, uh, time complexity is basically however large n is will be how long it takes approximately. Like it'll be correlated. And for space, in this case, it's literally like it's not even related to n at all. Like the space used is literally we're using sum to store like a number, and like we're using a local variable for I to like iterate through the numbers, and that's what it is. So we're literally just storing two things. And like if n is 1,000, we're storing two things. If n is 1, we're storing two things. So space complexity would be just like 2 in this case. So like basically the space complexity of 01, because you basically scale it down to like a constant like of 1. So you don't care if it's two things you're storing or 10. But we don't need space complexity at all. Like I don't think Java taught it. But if you're interested, so I could actually, yeah. So I think in the passive, like for anything it wants the big O, it usually just has a print ready for you which you copy paste, or like it might be even part of the code you copy paste. It's like they just have like the time complexity of R square. is, and they put like, and then they like in the actual like paper, the actual document, they just tell you replace xxx with like what you believe the time complexity is. And for r square, because we're going through n numbers once, it is O of n. If we went through it another time, if we did this, I like replace the loop variables obviously, it'd be n squared, because for each n, for each value in n, you're doing it another n times. And then basically with nested loops, it's literally just like you just increase the power. The more nested loops, the higher the power. So just one nested loop would be a power of 1. So just n to the 1 or n. And Jay said to be careful of if you have a function call inside here. So if I do like a function call here, just ignore the context of the question. Just like if I put sum in here, or if I just call something here that also does a for loop based on n, that'll be one for loop in here in this function, but also another for loop in here in this function. So that'd be 2 nested for loops. So in this case, it would be n to the 2, n squared. Yes, and same for the recursive one. It is n as well. So it just does it n times, but it makes a stack frame for each one.
Right, so each time recur. Never mind.
Okay.
Recursion usually just n then?
It depends. Like, I mean, there's binary search, which is log of n, because you know you're reducing the problem. You don't need to do it n times.
Yeah, that's padding.
Like usually the recursive algorithm has the same time complexity as the non-recursive like variant.
Okay.
So like if I do like another algorithm and I make a recursive version of it, the time complexity should be the same, unless the recursive algorithm is more efficient, which usually it isn't. It just looks nicer. Like this will be slower on average than this for like large numbers, because you know the stack allocation takes a long time. Like it takes some time. It is fast, but then as n grows, like it'll be a bit of a gap between the two, even though like n stays the same. But then the order is about like the big O complexity order is the same, because it just grows as n grows with like a certain rate.
I'm looking at
I've,
test 2 right now.
what?
I'm looking at what you call it, test 2 right now. So it's binary search, is it? Or
Yeah, binary search is log of n, because yeah, you know it's half the problem, and then quicksort is n log n, because it halves the problem, but also like for each piece it goes through the piece, like the length of the piece, but then if you sum up the pieces, you get the whole length, which was n. I'll get to it in the actual sorting practical if I do it. Not today though. So the next question is binary tree search. I probably need to download the binary tree stuff. Or find another place. I should have probably made a new project for this. Do it now.
So the next question involves the tree header. So you would have to download it and then place it in the same project and also include it. treenode.h. So it tells you to do that here. So create a Boolean search function. Searches a binary tree for a key and returns true if the key is found, false if not. And it's a templated function because of this t in here. The parameter of the key can be different because the tree is also templated as well. So it can take any type, or at least any primitive type. So they didn't tell you to put it in, but you have to for it to work. Declare it as a templated function. Template type name t. So we're gonna search. Oh wait, I'm being stupid. Yeah, it said to. Yeah, did. I was wondering why tree isn't passed in. This already implements it because like I grabbed the header not from practical, but like from other practical. So I'll pretend I'm doing it from scratch. So you add the function definition here. Pretend it wasn't there. I just added it, and then ignore it. So we've declared it here. Now we implement it. It's a templated function and the scope resolution modifier to make sure we're like redefining the search in tree. So what we have is the current node, I think, in tree. I just have item. So first thing you can do is check if item is equal to the key. If it is, we can just return true. Like if we're already in the node, because the way the tree is constructed, it's just a bunch of nodes like linked to each other. So like linked up the way to the parent node. So then if we didn't find it in the current node we're in, we tell like either left or right node to look for it. But we can be smart about it because we can like think, because it's a sorted, it should be a sorted tree, so it should be ordered in a binary tree. Like left subtree is always less than the right subtree, and it's less than the root node we're at. So we know that if the key, so else if we didn't find it, if the key is, let's this way, if the key is less than the item that we have right now, it means we need to go left to go to the lower items. So we would return left tree search. So like if we didn't find it here and we know it's less, we tell the left tree that we have a pointer to search for it itself and return us the result. Where am I at? Here it is. I think depth is another thing we need to implement later. And then the opposite would be if key, basically if key is greater than item. But you can actually get rid of this because it'll always get there if key is greater than item. Because it's either equal to, it's either less than or greater than. So you can have an else. So this would be a right tree. Do you want a diagram for me to like explain it better, or you okay with this? At least someone say something.
Would this only work for ints, or
This is templated.
always
You mean the comparisons?
Or basically the way it's implemented is, does it have an insert thing? It doesn't really. Like this here, like this class here doesn't handle any inserts on its own. So like that's why we have code to insert into it. Like in external, like in here, we would write a function to insert stuff into it here to make sure it's sorted. So you would just like to insert something, it'd be something like insert t key, and then what you would do is you look at the current node, and if it's less than, you would like place it on the left. If it's greater than, you place it on the right. So you create a new node and then put it into the left tree or put it into the right tree. But like it works for any primitive types because they all support like comparisons. But then for an object, you can just override the operator. You need to override those three, I think, for it to work. So you could just have your own type, just like custom integer. So if t was custom integer, and like you have those operators redefined, it will use them. For strings, what it does is if it's a tree of strings, it like sorts them alphabetically, but it's also case sensitive. So ABC with lowercase comes after ABC with uppercase, because it's literally just the way ASCII works. ASCII table. Yeah, and then the way it is just there's a nice small one.
Hoping they don't give us that one. That sounds painful.
Yeah, so here's A at position like ASCII index 41, and like lowercase a. Oh, and here I don't think it's ASCII though. Yeah, here. So A at position 41, and then lowercase a is at 61. So it literally just compares the ASCII code for the strings. So it goes for each character and then sorts it alphabetically by looking at the first character first, and then if it needs to, if there is the same character for first character, it looks at next one, so on. Those strings are sorted alphabetically, and then capitals before lower cases. So we implemented the function, we could probably test it. So I would just create a tree. I wish you could grab some of their code to create it. Yeah, they tell you to create a tree of weekdays. I'll have it open on my side monitor just to see it. And basically this tree is sorted by title as well. So it's not sorted by like the order of the day. So what it has is Friday starts with F, Monday starts with M, F comes before M, so F is on the left, Friday is on the left, S comes after M, so it's on the right, M before S, so it's on the left, and so on. And basically anything you look at will be in the right position, like sorted alphabetically. And they give you the structure, so you don't have to worry about like in what order you add it in to make it balanced. But if you just like add it in whatever order, like if you just added them in the order they're in, like it would be like Monday at the top, then Friday because it's less than it'd go on the left. Like Tuesday it's greater than M, it'd go on the right. So it'd be Monday, Friday, Tuesday, and then like Wednesday be greater than M, so it'd go to Tuesday. It's greater than Tuesday because W goes on the right. So it'd be a different order, and I think it wouldn't be balanced then. There'd basically be more days on the right of Monday than on the left because there's more days that start with like a higher letter than Monday.
Is that going off alphabetical or literally just days in a week?
This? No, this is alphabetically. This is basically the string sorted by like the string, like alphabetically.
So basically, to recreate this, you know that you need a node of Sunday that is connected to a node of Monday, that is connected to a node of Friday and Saturday, and like a node of. So what you usually do is you start with the leaves because they're not connected to anything. So to create them, like the constructor takes pointers to other nodes. So first you would create nodes that don't need any pointers, and then you would create the nodes above and be able to point them to the right node if you're manually creating this tree. So tree node string, and also those nodes will probably have to be created on the heap to make them pointers. So that you can pass them in as pointers to the constructor. That's what the constructor takes tree node pointers. It's called Monday. Yeah. And the constructor takes the value, the item type T, and then the pointers. So I'm gonna have null and null for it for now, for the 2 pointers for all of them. See, like the problem with this practical is like there's literally so much just copy pasting to do, and it's literally little of this is actually coding.
That sounds like a positive in some ways.
Well, I mean, I'm kind of limited in time to explain it because I'm just copy pasting stuff.
Is it just me, or tree algorithms simpler than the other devs think?
They're quite okay. Yeah, I mean they're recursive, which makes them hard, but then there's less, like they have less functions in general because they're more like a structure that has like no like little of its own functionality, and usually like any functionality is like added on top of it by using it. Whereas like a list, it has a lot of its own functionality, like get an item at a certain position, or I mean you could add a method here into tree to like get an item at a certain position. That'll make it more difficult. Like they've added a like a depth method to like to find the basically the height of the tree. So like depth of one node is 0, depth of 2 nodes is like with like a parent node and child node would be 1, and then basically the lower you go in terms of parent child nodes, you just increase by 1. So like this one has a depth of 2, like 0, depth of 1, depth of 2. Basically the number of steps you need to go down the tree. To reach the very last node. Now if I look at this, Friday needs to be created first, and Saturday, so that I can create Monday, because I can't create Monday without a pointer to those two. So I wish I could move it. Oh, I can't. Forgot about this. So Friday and Saturday we're creating. And Monday can be created by pointing to Friday on the left, to Saturday on the right. Just like this. We can do the same for Tuesday. Tuesday points to Thursday and Wednesday, so they need to be created before it.
I'm guessing. Oh, never mind. I thought this would have to be strings Friday and Saturday, but I think I just spelled mine wrong.
Those are pointers. Like I named them the same, but like they could be like this. I'd have to rename this. And then the very root node, Sunday, just points to them too. Yeah, so Monday on the left and Tuesday on the right. Now we got a tree, right? And basically, if we grab one node, that node can basically represent a subtree. So if we grab Friday, all we have is this node because it doesn't have a pointer to any lower nodes, and it can't get its parent node anyway because it doesn't have a pointer to it. So we can grab a single node, add the leaf, and it'll literally be just one node. If we grab another node like somewhere else, like Monday, it has pointers to those two, but no pointer to Sunday. So what we have is basically a subtree of the whole tree. So we'll have those free by grabbing just Monday because we have pointers to those two from Monday, from the Monday node. Same for Tuesday, you have pointers to those two. So when we want to work on the whole tree, we want to grab the root node. For us, it's Sunday. So sometimes it's a good idea maybe to name it root node rather than like the data it holds. So now on any of those nodes, we can call like this search function, but that means that it only searches in its subtree because it can only go down the way using the pointers. So if we search in Monday for Sunday, it can't find it. If you search in Tuesday for Monday, it can't find it. So if we want to search a whole tree, we search using the root node. So Sunday, because the pointer, we need the pointer operator. Search, and we would basically search for each of those days to make sure they're in here. I know I'm doing single quotes. Just more copy pasting. And then you'd probably want to search for something that's not in there to make sure it can return false as well. Yeah, it's trying the wrong thing. It's great. So see this project is in bold. This is the one that's going to try to run when I press F5 or when I just do like build or a debug, start debugging. So what you want to change is in the solution, properties, change to this, current selected, and then it'll basically be always in the one that's selected in bold here. Otherwise you switch it in here, if in this drop down list. Now it runs again. Oh, build errors, nice. Left tree is a pointer, right tree is a pointer, so it needs to use those operators to search. And I forgot to pass in the key to allow the subtree to search for this key as well. More errors, let's go. So when you have like a runtime error, it's a good idea to just go to the call stack and see what is happening. So the very last one, inside search in line 42. We are not checking that. Let's say we're at the last node. So what it did here, it got to Sunday, it's our first call, and searched for like that very like that string we don't even have in the tree, that weird one. So like that weird one starts with 1, and like 1 is like a very like low character.
So it's going to be less, so it goes to Monday. It compares it to Monday. Like 1 is less than M, or like whatever, that whole string is less than the string Monday. So it goes left 1. And compares it to Friday. That whole string is less than Friday. And it tries to go left, but there's no node on the left. So what Friday has, it has those two equal to null. And what I did is I tried to call the search function here where it's null, and that gave us that exception. Not sure why I didn't say like null pointer exception. So what we need to do is to check that left tree isn't null. So we can do that in the same check because it's related to just this if. We can check that left tree doesn't equal null. And it also means because we need that check in here, we need it for right tree as well, so I can change it back to an else if. Change this to and. Copy paste, more copy paste. And then basically what will happen is if it finds it, it returns true. If it like doesn't find it but there's like more left nodes, it searches on the left nodes. If it doesn't find it, like if it's greater than, it searches the right nodes. But if there's no like left or right node, so basically in the else you can return false for sure, because you know that's the very last node we reached. So in our case we get on Sunday, Monday, Friday, and then there's nothing more to reach. So we can just return false because we didn't find it. And it's guaranteed that if we didn't find it because we were always going in the right direction, because it was like a sorted binary tree. We were always going in the right direction, so it couldn't have been on the right when we went to the left, because we know for sure the ones on the right are definitely greater than the one we're looking for. So when we reach the leaf node, we knew we didn't find it, if it's not the leaf node. So we do that. Oh. Still an issue. Maybe I just didn't close it. Yeah, so this time it's still fine. So the way it prints booleans, because this search function returns a boolean, it basically prints it as a number. So 1 is true, 0 is false, but really like anything but 0 is true. So if I do like if like anything but 0, and I want to then print it, sometimes like it gets stuck because like my cursor was pressed here, so it didn't print anything because it was waiting some input from here. So I had to like press enter once to allow it to print, and then the cursor moves to here. So yeah, it prints it because like it interprets anything that's not 0 as a boolean. So if I press have 0 here, it will not print anything. I understand. That's a bit of extra information.
Here, in the key string, it says Magnus, the search function is in the member. What do you have something up in the public or something?
In the H. Well, first you declare it in here. Got that?
Oh, sorry.
Okay.
I didn't have Boolean.
Alright. Yeah, it has to be like exactly the same like function prototype. It has to match, like a header of the function has to match exactly for when you define it after the declaration. Also remember this one here. If you just do this, it will not have a problem, but when you go to run search, it's not defined. Because what you did here, you just defined like a random function in this header, and you know the way I said headers literally just get copy pasted into here. So you grab everything in the header and you paste it into the start of this, like literally into the place here. So what you'll have this function here. So to call it, you'll need to just do search, and if you do tree search, it'll do nothing. That's why you need the scope resolution modifier.
What did you say to swap to a different project?
Solution. So like up here is your solution. Those are your projects properties, and then you can either choose it here, choose which project you want to do. I always do just current selection, because I just know whichever one is bold is the one I'm going to run. And it's always going to be selected. If I just go here and just select this file, it just switches to it. So if I was editing this file last, this will be the project it's going to run. We're getting close to the end of the hour, and I have not really done much.
I got a lot of errors.
Oof. I don't know, like def is literally pretty similar to the search thing, with the exception it'll be a bit like something like this. So you would have a sum defined, and then at the very first node, at each node, the sum is 0. But then if you go lower, you add 1. They actually have it defined, so I'll just show you here. So DL is like, I don't know, depth length. I don't know what they want to say here. Oh, so that's depth on the left, that's depth on the right. So on depth it's called on node. It's like it initializes the depth of the left subtree to 0, depth of the right subtree to 0, and then basically if it has a left node, it asks for its depth, because it's not aware of how many, like Sunday's not aware of how many nodes are below it. It just knows it has a node on the left or right. So to get the depth, what we can do is ask how many, like what's the depth on the left like, what's the depth on the right like, and we always choose the higher one because like the highest depth will be the depth of the whole tree. So if this had another node, depth here would be 0, 1, 2. Depth here would be 0, 1, 2, 3. So you would get the biggest one to get the depth of the whole thing. So if there is a left tree, we call to get the depth of the left tree. If there is a right tree, we call it to get the depth of the right tree. If there wasn't any of them, it would just stay as 0. And we always return just the highest of the two. So if DL is greater than DR, DR is larger, we return it. And let me see. I think they add 1, so their numbers will actually be higher by 1. Or will they? So if I just do the depth of this thing, instead of 0, 1, 2, it'll go 1, 2, 3. And it starts from the end as if any recursive thing. So Wednesday will return. I'll just run it to make sure. I think it'll be one higher than how I count it. Let's do Sunday depth. I'm getting some nice errors here. Oh yeah, it was showcasing why I can't remove this. Yeah, so they return free. So their depth is free. Here's the depth function you're asking, but I decided not to show it. Decided to just explain it. Depth of an empty tree is 0. But to me is like a tree of one node has 0 depth. A tree of like a node and like another child will have 1 depth. I might need to double check it.
get the image up.
Yeah, so the root's depth 0. So the further down you go.
Yeah, but like the way they return it, they have like, even if it's just one node, they make it 1. But then like any diagram you literally go to, it's like 0, 1, 2, 3. But there's would return 4, 3, 2, 1. Because they always add 1 in here. That's their code that I just grabbed with the header. So if it'll return the depth of its subtrees, if it was just 0 on both sides, it'll just return 0 plus 1. So that's the minimum it can be. It'll like a minimum it can be 1. If you just return this, you would need to somehow increase it at the root. So with each return you'd need to increase it. So if you do this, leaf nodes will just return 0. But you would need to return the leaf nodes plus 1. You see. But I think like if they want it this way, you better stick to this way. I'm not sure if they actually said which way they want it. I know I'll have a bit of time to show binary search maybe. So they want you to write this function. And basically they want you to construct a like balanced tree from those like numbers. So they like it's hard coded numbers, so the function doesn't take the numbers as a parameter. You're told to use those numbers in here. And you'd need the insert thing. Oh, basically to construct a balanced tree of like some random numbers, you'd want to order them to know which ones are larger, which ones are smaller. So 7. So first you'd order it, and like for this question, you just order it because it's a small number set. You just order it yourself. Otherwise, you could probably call if it's like if the question involved like some sorting before, you could probably just call the sorting algorithm to sort it for you. And what you do is you always start in the center. So what's the length like? This is index 0, 1, 2. So you start in the center to find the center. I mean, you could either like look for it, or you could just take the index. So if you were to do programmatic, you'd take the index of the last thing, index of the first thing, add them together, divide by 2. So 6 plus 2 over 2. And you would always do integer division to find the center. So it'll not have any fractional part to give you like an integer index you want to look at. In this case, it'll be 3. So we're looking at index 3, that's our middle number. So what we would do is we would insert 17 into the tree. So this is pseudocode for now. I'll need to implement the insert method for it to work. Well, the first thing you can do is create just the empty tree node. This will be the root node we start from. Call it tree. So we've inserted this, and that'll be our root node. If I just grab this again, it got inserted. Now what we do is we look for numbers less than it, and that's basically all the numbers on the left in the sorted array. And we look for their middle. So in that case, 0 plus 2 divided by 2, 1, so 7. And we insert that. And the way the insert function will work is like it always inserts smaller numbers on the left, bigger numbers on the right. So it'll insert 7 on the left. Then what happens next is for 7 we look to the left of 7. We find, because it's just one number, there's no middle is 6, so we insert 6. And because we got to basically the very left, we can go back to the right. So what's on the right of 7 but still on the left of 17? There's 12. Now we go to the right of 17 and it's just those numbers, and we go to their middle. We can insert 29. What's on the left of 29? 23. What's on the right of 29? That. And that'll basically be how a tree looks, but then now if you look at it, it's always a smaller number. It's on the left of a larger number. So like the order we do it in is insert 17, which is the very middle, insert 7, which is the middle of the left side, insert 6, which is kind of the middle of the left side of the left side. They would be really nasty if they told you to do this. If you remember in what order I did it in, 17, 7, 6, then 12, and to the right side 29. For the inserting function, it's in the notes, but they might ask you to write it. 23 then. So always insert left first. So like middle, insert left, insert right. But because we're kind of doing it recursively, so we insert middle, insert left. To insert on the left, we insert middle, insert left, and like because we got to just one number, we can insert it, and then right, and then recursively go back to this, insert the right, but then we can't just insert it. We need to look at the middle of those three numbers, so that would be this one, then left and right again. And I think if they make us do it, they'll not have more than 7 numbers, because like they don't want to waste your time too much. And I think the way the function is implemented there, it takes a tree as a parameter, but it returns the pointer to the new tree, or just returns it. I don't think it's needed. I'm gonna quickly write the insert function. It's in the notes, so technically you don't really need to know how it works. You can, if you can just copy paste it, really.
What did you say you do if you have an odd number for the indexes?
This is an odd number, so it actually works well. It's not of an odd or even. It's more about if it's a triangle number, it'll be nice and even. So 7 is a triangle number. You know those like the 1 is a triangle number, and then 3 is a triangle number because you know Pascal's triangle. If you do that, and then you literally just sum all the numbers in the triangle, and you go down a level. Be 1, 2, 2, 1. If it's say it was like this, so it's 8 or 6 6 this time. You can just like it'll be index 5, index 0, like divide by 2 will give you 2, and that'll be this number. So it'll just be like 1 below the middle, because the very middle is like at 0.5. Yeah, it'll round down for you, because what you're going to do is you're going to grab the index, which is an integer, grab another index, which is like start index. Why is it 2? It should be 0. And divide it by 2 to find like the average, and the average will be the middle, and it'll always give you an integer. So this was 5. This was supposed to give you 2.5, but if you didn't cast it specifically, if you didn't cast any of those specifically, and you just had them as like the index and then 2 in here, if you made it 2.5 or 2.0, it'll be double. Now it'll give you 2.5, but if you just make it like this, it'll give you 2 without the remainder, and that'll make it point to here. Insert. Could probably make it templated. And then the key, so or value you're inserting. And I think we can, alright. So basically if you pass in an empty tree, we can create a new node with the value passed in, because you know that value is not in the tree yet. And basically the thing of binary trees, like all values in it are unique. So all node values are unique if you want it to be like sorted, because you can't afford to have like another 7 here, because then that breaks the rule that right is always less than left. Right is always greater than left. So if the tree is null currently, we can basically create a new node and give it the value. And it doesn't really have to point to anything. So like the first thing that happens, tree is null, gets passed in. Why is this not liking it? There's a string tree. And yeah, so first thing that happens, tree is null, gets passed in of 17. We create the new node with the value. After that, tree will be different because we passed in the pointer, and that's why they return this. In the notes, they return the actual pointer back. To be able to reassign a pointer, you either want to pass it in as a reference so that the pointer doesn't get copied,
because then you're only changing the copy, or you want to just return it back at the end of the function, which is why they do it. Forgot about that. So now that it returns something, you would want to store it in the tree every time. Basically, because we want unique values, if we pass in a value that is already in the tree, so if we're at the node with the same value, where the item is equal to value, we can just return the same tree, so it's already in the value, we don't need to insert it. So technically I don't even need this line because it does nothing. So I'll comment it out. I need to consider other cases where, because the node we pass in is always the root, so in this case it's always the root. We created it, gets passed in all the time, it gets reassigned all the time, to get updated, and we need a way to search like the tree, similar to how we searched it here. Let me see. Yeah, so you know the way you search it recursively because you can only search it in the node, and then you pass it to the subtree to search it. It would do the same thing here, but I don't think we can really use the search function because we also need to insert at the right place, but the search function will just tell us it's in the tree, but it doesn't tell us where to insert it, so we kind of need to repeat this to insert it at the right position, insert the new value at the right position. So we're doing that check we did in this search. I could most likely just copy and paste the search, kind of save some time. So, well, it didn't save time. Oh, okay, so tree wasn't null because we considered that here. So the tree, like the node we're at, the root node at least has some value, and we can compare this value to the item. So to the item in this node. So tree item. So if the value is less than the tree item, what we do is we just tell it to insert into the left tree this value. So basically, if the value is less than the like the current value we're on in the tree, we tell it to just go like insert it into the left of me, but I don't tell you where to insert it because it might need to go even lower. And we also need to check that the tree has a left tree to be able to insert it there. Otherwise it'll just return from the function. Right tree.
I'll probably test it now. Is there a print function I could use? Nope. So this should work. So the way I've tested is I'm gonna this function should create the tree of all of this inserted, so I can at least just make sure they're all in the tree when I search it. And I want to search for each of those numbers. Like if only they had like the print method implemented in the tree, which is also one of the past paper questions. You're asked to print the contents of the tree. Like I could just print the tree to see that everything's in the right place, and it wouldn't print like this. It'd probably just print like uh, depending on what order you print it in. So it would just print like 6 on one line, 7 on one line, 12, 17. I'm not sure. I have not seen the notes on this. There's in order traversal. So that means when you traverse the node, you look at each of them in the numerical order, or like the order it's supposed to be in. As pre-order traversal, then you basically always look to the left of the node. So you start from the top, look on the left of the node, take 17, then you go down to the left, take 7, go down to the left, take 6, and it's you kind of need to draw like the silhouette of the tree to be able to use it. So you go like around the silhouette and you kind of hit the left, like from the left, and you would hit like first 17, then 7, then 6, then go up, you'd hit 12, go up again, hit 23. Oh wait, no, you go like this, hit 29, hit 23, hit this. Let me run the code. And there's also post order, which is like the same but opposite. So you always go on the right. So again, but you start from like left of silhouette, so you just draw it out, and you would hit this first, then you would hit 12, then you'd hit 7 because you're hitting from the right of the silhouette. Then it goes to the 29, but you don't hit it because you're on the left at the moment. Go around 23, go around 69, 29, 17. Got build errors, great. More build errors. Right tree. Last one. Return value. I made it recursive, yes. So basically you pass in tree. Let's say okay, it's null, and you pass in 17. So if it's null, you just create a new node, and like the tree is now literally the node of 17 to this node. So like imagine this doesn't exist yet. This will be the first node that gets created.
we pass in the tree, and we pass in 7, so we pass in this node 17, pass in 7. 7 is less than the current value of the node. So what we do is, well, basically in this case, because we don't have the left tree of 17, it's just like 17 with no left or right tree. We, oh wait, what do I do then? I probably don't need this. So basically, if it doesn't have a left or right tree, I actually do want it to insert this value in there. So this check actually prevents it. So if the tree doesn't have a left tree, if it doesn't have a left node, 17 right now, it doesn't have, it basically it'll point to null in both directions. What I wanted to do is like create a node on the left. So what I'll do is, without this check, I will just insert, and I'll pass in the left tree, which is for 17 it'll be null. So imagine we just have this now and it points to null. I'll pass in this null. It will basically create this node. It will return this node, and I need to add it. But instead of adding it to tree, I'm gonna reassign left tree, reassign right tree, like this. I think that will work. So in that case, what it'll do is it'll assign 17's left tree to 7, to a node of 7. And next thing down, 6. Again, what you're passing all the time is just this root node, this 17. It is like, what are we passing in? 6. So 6 is less than 17, it goes here. It calls insert on the left tree, so it grabs the left tree and calls insert on it. So imagine we just pass in this left tree in here. So now we're at node of 7 and the value is 6. So 7 points to null in both directions, and a 6 is less than 7, so we insert 6 at the left node. So what's going to happen is, in here with 7 and 6, again it's going to go in the left, so it'll assign its left tree to be the result of inserting using the left tree of 7, which is null, and because it's null, it's going to create that new node of 6, and it's going to return the node and assign the left tree to be that new node. So basically you're reassigning nulls in the left or right tree to be the new value when you find out where it needs to go. So we started with 17, we inserted 7 at the null pointer where it was pointing to the left, we inserted 6 at the null pointer where 7 was pointing to the left, then we inserted 12 to the right of 7 because 7 used to point to null, now it points to 12. Same for 29, 23, that gets inserted at the null left pointer of 29. Like, just need to print it. So it doesn't find one of the numbers. Which one? Do I even insert it? I don't. Now I should find all the numbers. And yeah, this would print true or false, so what you could do is like just put it in the if and then print true if this returns true. But it's going to be numbers and you kind of have to know what they represent. So 1 is true, 0 is false. Is there anything else you want me to go for in this practical? There's sigma, maxnum, print I could go for as well.
Could you show me the order of what's did there for the searches?
Oh, search. Oh yeah, that's binary search, isn't it? Pretty sure it is. I know. That's fine. Like I can submit the code. So where am I at? Search. Yep. So the order of this would be, because you know the way you kind of always cutting the problem in half of those, like recursion, like in binary tree especially. Uh, what you have all the time is you compare it to the node, and if it's if I just go show here, you compare to the node you're on, and if it's less than, you literally just discard the right tree because you know it can't be there, and you look at the left tree if it's less than this node. So it's always cutting the problem in half. So
Size of the tree, that's more than cutting in half. So for complexity, would it always be uh, it's log n, but if it was half, it'd be a specific number.
it's never a specific number, it's literally just order. Like a specific number, like you can't really get it. You can get an average of the specific number that it takes. Like for, let's say for 7, right? To look for 7, we need one search. Like we need one iteration to look at 17 and compare it. Then from that we'll go to the left, discard this, and like just one iteration to go to the, like to compare it to 7, and that like we find it. But I think for complexity we always think of the worst case, and the worst case is literally always equal to the depth of the tree. Because let's say the worst case of searching something is you either don't find it or it's at the very end of the tree. So like for our tree, the very end is like here. Any of those numbers would be the worst case.
That's what he was saying, that it was quite efficient though.
It is. So like, say we're looking for 6, compare 17. 6 is less, but it's not equal to. So we discard the right tree, we look at the left tree. That's one comparison, that's just one iteration. We look at 7, 7 is greater than. So we go left, and then we find 6, so 1, 2, 3, and that's equal to the depth. And we have 7 numbers. Log 2 of 7. It's more like you take n, add 1, and then you take a log, because then like number works out very well. Or like you basically bring n up to the nearest power of 2. So if our case n equal to 7, we bring it up to the nearest power of 2, which should be 8. Like 2 to the 3. And then if we take log of base 2 of 2 to the 3, it's 3. And that's like the worst case we need to take, so it's literally just the height of the tree. And I think it wouldn't be the height I'm talking about if like starting at 0, it literally be like 1, 2, 3. So like just the way it works out, like if I expand the tree I still want to. If I just add like more like nodes here, just imagine those numbers work out. This time if I want to like find something at the end, or like I would go down 1, like compare which way I need to go to the next one, compare which way I need to go to the next one, and then go to the last one, and that'd be 4. So in this case it's like 7 plus 8, so 15. It actually might be just plus 1 instead of just going up to the next power. So with 15, you add 1, that'd be 16, which is 2 to the 4. So log of 2 to the 4 will be 4. And that's our height again, height of this tree. So it is just log of kind of n plus 1, I think. That makes sense. But because we don't care about this coefficient, like plus 1, we'll just put 2, like log of base 2 of n. And like with computer science, or like with time complexity in computer science, you just assume that log is always base 2 log, not base 10. I think that's how search is. Just I'll write it here.
Yeah, in the questions, it says using dynamic allocation. Are you just supposed to just manually make that, or is it supposed to be able to work with any list of numbers?
Um, Dynamic allocations, they just mean that I basically created the nodes on the heap. If I was to create it on the stack, like you know, once it leaves this function, this gets deleted because it's on the stack, and it's basically in the stack frame of this function. So when the stack frame pops from the stack, it deletes like those local variables. So that's why you want to create it on the heap here. Oh, where am I at? So that those nodes go in the heap and then you have access to them even after you leave the function. And then here you would, because it didn't take anything as a parameter, it just expects you to create something here and return it. But if you create it on the stack, it'll just get deleted. So you create it on the heap by just using the insert, because that'll create the very first node in the heap and then like the sub nodes on the heap as well, and then you return the tree. And where you store it is you store it in a pointer that points to the heap where BST created it, and where insert created those nodes. Is that what you asked? I might have been off there, off your question.
Well,
Like for
no, I think I understand what's going on anyway.
okay, like like for this question specifically, they didn't want us to like write the algorithm to do those, like to find out this middle and stuff. But you technically could, and it'll work.
So long as he accepts that if the similar question comes up and he accepts brute force methodology and he doesn't
Yeah.
spend any effort in order to do it automatically.
I think
Some sort of cheat sort, some method.
I don't know. This session's been dragging on for a while. Do you want me to do one of those two? Like either? Or do you find them okay?
Maximum numbers just go down to the very most right side, is it not?
Hmm. In a balanced tree, yes. But oh, is it? It might be. I think like this one kind of assumes it's not a balanced tree because it shouldn't be that easy.
Hmm.
I'm sure
So
like
do those both require you to scan through the entire tree?
yes, sigma is just sum. So like you're literally adding the sum of each node. And max num, like it depends
So
if
zero
it.
is the root.
I mean, it does say it takes a binary tree. Yeah, it does assume tree's the root, but then it's going to be recursive. So again, like you'll pass the subtree in here when you need to recurse. Like the thing of trees are like most functions are always just going to be recursive.
If you have a recursion for the leftmost and then the rightmost, you can just have it so that it just scans through the entire tree and keeps comparing until it's done.
Yeah, for maximum, you're always going to be just going right if it's a binary tree. I think I kind of misread that, and I like when I was doing the practical the first time. I just kind of did like just the maximum number is just on random tree. So like if it was not balanced, where am I at? So if it was like this, and I was looking for the minimum, and you obviously don't want duplicates in there, what you would do is like you'd have a variable saying minimum equals to like the current node you're on. Then you'd look at the left minimum and right minimum, And if they're less, like whichever one's less, you assign minimum to be that for this node. And it's going to recurse using that, so the minimum of this will like first be 7, but then when you look at left and right, so like this is all assuming like it's not ordered at all. So like assume there's just random numbers in here. I might code it just real quick. It does say it wants it templated. Yeah, an int one. Whatever sigma and max num. So first we would say the maximum is like the node we're on, because we don't know about any other nodes yet. It's item basically. And what we would do, if tree is null.
Okay, yeah, just follow us right. If
Yeah, continue.
no, I was just yeah, if tree right exists, then you change max to that one and keep going till you get
Yeah.
to null.
I was gonna like protect us from null being passed in. So if nulls gets passed in, we're looking for max num, right? So I like basically you want to return something that is definitely not gonna be max, right? So if it's null, you just want to return like some invalid number, which can not be max. So what you can actually use is like int max. If you're using int, of course, like a negative of int max. Cause like, what are the odds that this is like the largest number in the tree? It's pretty low. Like it could return -1, assuming like your tree is only just integer, like positive integers. But I like thinking of int max, just in case you have like some negative numbers and you want to account for them being possibly the largest one. So when you're at the null, you're literally just gonna return like some very invalid number to make sure like it doesn't affect the maximum. So then the max equals tree item, and then yeah, you probably want to store left max. So you're literally just gonna call this function. Wait, was that function in tree? No, just outside. So you're gonna call it in the left tree to find whatever's the minimum, maximum in the left tree, and same for the right tree. And then you basically look whichever one is greater, you reassign max.
You got max at t then.
Thanks. And one recent thing I started doing is actually use like one line ifs. I kind of started bringing them down to the next line, because if you get an error in there, like I saw it in some video and someone told to do that. If you get an error in here, like you don't know which of those two caused the error, but then you know if the error occurs here or here if it's on another line. It's kind of useful. You might get stuck on that. So like if you see an error here, you may want to like bring it down and then run it again to see like which one specifically causes it. Instead of reassigning, you probably can just return it, because in the end you're just going to return max. So
like if you're gonna reassign it and then return it, you might as well just return like whatever you're gonna reassign it with. And then otherwise, like if none of those were bigger, you just return max. So this should work, and we actually have this thing we can test it with. Yeah, also remember to delete whatever you create on the heap. I've not done that. Yeah, it's like, see if you did this and you didn't delete any of this at the end. And to delete it, you can just delete the root node. It like cascades the delete down the way. Because when you delete the root node, it goes into the destructor in here. And like that deletes the left and right tree for you. So you don't need to go and delete those like left, right trees. You delete this, it deletes those two. This deletes those two. This deletes those two, and like basically deletes the whole tree if you delete the root. Yes, like that's part of the code, yeah. Like I mean, it's part of the destructor in.
So that it calls
Yeah,
the same destructor to the left and right.
yeah. Called maxnum to that. There's it's empty. And yeah, it's correct because remember that was our tree. That's the greatest number. But I mean, again, like this is not what a question actually asked for, because like technically you could just go right all the way and get to this number. But like this will work if I like make it unbalanced. Like if I just
So that just works on an unbalanced tree then.
yeah,
Okay.
this one is balanced, but like yeah, that's what I did. If I just like literally add a bunch of those, like there's no way this is gonna be balanced. Like I can even mix and match it, because it's only balanced because I like inserted them at the right order. That's the only way it's balanced at the moment. So if I even switch two of them, like that search max won't work anymore if it just relies on just going right all the way all the time. Say like I moved this like somewhere. I see the way insert works. It like it balances it kind of. Not doesn't balance it. Like it makes sure it's sorted. So if I use insert to insert it, it makes sure it's sorted. But if I just did this, right, and I did not like link it up to be sorted, like going right will not find me the greatest one. If I did insert, like just the way insert works, it always just puts stuff that's greater on the right. That's the way we did it. Like if it's greater, insert it on the right. So I actually can't like mix it up for it to not be sorted, but it will not be balanced because like if I just add a lot of stuff that's greater, what it'll do is it'll just keep on adding stuff here, and then there's still like little stuff here, so it's not balanced. So what you do is you would grab all the numbers, sort them, and then just do that thing I did to make it balanced. So I think maxnum works. We could literally change it to min number easily.
I don't know if this typo might be seminar.
Yeah. Well, some of a null one, it's a nice easy one. You can just say 0. So just return. I could return -1. Well, 0. 0 is more correct, I guess. And then we can make it equal to the first item in the tree, and then some, like, you don't even need to compare this. Now it's even easier than max, because max you need to compare to make sure it's a higher one that gets returned. This one you're literally just adding the result of this of the left tree.
Same for right tree. And this ensures that at the null of the leaves we just return 0, so it doesn't affect the sum. So I assume it's right. 13, 30, 42, 65, 94. No, I already got it. 94 plus 69, 163. And just the numbers are kind of nice, like they add up well. But yeah, like if it was like as it is in the question, you literally just go right all the way all the time. So if tree equals null, return like whatever, and then otherwise int max equals tree, and you just go right all the time. So you would return like if I was to rewrite it. So if the right tree is null, there's nothing greater than it. So if what am I doing? You would return just the value, because you know there's nothing greater than this value. If it's a balanced tree, it's balanced like sorted tree, and it doesn't have a right node. Otherwise, if it does have a right node, you literally return max num with the right subtree, because if you just return the right node, that might not be the very last node in it. So let's say we're here, we're looking for the largest number. If it's literally like this, we just return 17 because the right node is null. We just return 17. Otherwise, we return the max of the right subtree. Because if we just return 29, that's not the max in the whole tree. That's just the max in this tree. But we need the whole tree. So we would do, again, we would call max num. We would return the max num of this subtree, just this right side. And then again, if you do that and there's no more nodes after 29, you just return 29. Otherwise, you'd return the max num of the right subtree of 29, which in this case is just one node. So the other right of this is null. So we just return the value itself. So we either return the value if there's no greater than, or we return max num right tree. Well, and you probably want some null check in here, so just copy and paste that in. That's probably what they wanted. So you better read the question, unlike me. So I'll label this.
So, minus int max is just in case there's negatives in your string.
Yeah, basically if it's negative, you kind of like if I just return -1 here.
It could mistakenly be arbitrary with actual -1.
Yeah. So let's add -1 here, and let's say all the numbers before it until I got to this node, until I got to here, or like all negatives. Let's say this is all -6, -17, and it'll basically be in reverse order then, because you know like negative, it'll actually sort like so the 29 would be here, the 12 would be here because they're all negative, so -12 is greater than -29. So if you get to the very last node and it's null, so if you get here and it's null, that's this here. If you return -1, like it's greater than like the other numbers. It'll probably be on the right side because we get to the right side eventually. And it's not a valid output because there's no -1 in the tree. So technically the greatest negative number here will be like -6. So I also want like literally the biggest possible negative number. Make sure they don't interfere. So now just this code will run if it's a balanced tree, a sorted tree more. Yeah, just naming of those things is so weird. Like a binary tree kind of always assumes it's sorted, but then it may not be balanced. And to balance it, like this is exercise kind of to balance it.
I think that was everything Patrick was going to say.
Yeah. But like it took me 2 hours instead of the one I was planning to spend on it. Like I mean, I wasn't planning to do all the things.
And also, what is it, 3 times speed? It is 1 hour.
Yeah, but like I didn't want to sit here for 2 hours. um, yeah. So this is for binary tree. Left, less, and right. Any tree. Well, any tree basically. Well, any tree with only left and right ones, because you know the way a tree can actually be can have more than more than two child nodes. I think that's it. And